Good morning, everyone. Thanks for not joining. Today's talk is about memory recycling on network interfaces in the Linux kernel. So let's start on a bit of why we did this. This has been proposed in the past. This is not the first time we're trying to do this, and we failed in the past. So kernel used to have an SKB recycling on some of the drivers, which got very little interest over time. It had various bugs that we didn't manage to fix, and eventually it got removed. The driving force that made us do this is that many high-speed drivers, Mellanox and Intel usually, high-speed drivers, are already recycling their pages. Because they figured out this really gives them a speed boost. But everyone is doing something similar, but there's no common API for this. The next thing is that we also need to support XDP. XDP is kernel express data path, which we're trying to support, and at the moment what we end up doing is that we tell the driver authors to write an SKB-based driver, and then we ask them to shoehorn XDP support, which ends up being really easy, really hard. This can vary. If the original memory model of the driver was close enough to what XDP wants, this might end up being fairly easy, but if it's not, it usually ends up to a complete rewrite of the memory management of the network card. So by doing this on an API, we're probably trying to fix this as well. XDP wasn't part of the kernel in the past, and it now is, and it's gaining some motion. So the driver model should really change. The driver shouldn't really care if it's an XDP or an SKB buffer he's looking at. It should be relevant. It should be just a buffer, and then it should be handed over to the right kernel interface for further processing. The API is also trying to provide the network interfaces with DMA mapping capabilities. So if you use the API, you'll allocate the buffers for your network interface, and you'll get the DMA mapping for free. Now, the reasons we did this is that high-speed interfaces more than 40 gigabit are really challenging the page allocator at the moment, and this is pretty much the bottleneck we're seeing. The first bottleneck we have is this. We know that constantly allocating and freeing buffers is expensive, and this is going to get even more expensive when the SMMU and IMMU kick in. And the more the speeds go up, this is going to get even harder for the memory to keep up. Now, this is pretty much how modern network cards work. This is not this is not the same for every card, but this is pretty much what they did. You receive the frame, then you prefetch the descriptor. Okay. You prefetch the descriptor, you modify what you prefetched, the data gets written in the the first thing is that the data is copied over on the memory, on the host memory, if there's space. Then you modify the prefetched descriptor, and then you notify the user space that you have a new network buffer. So if you think it as if you take some time and think the steps that are needed for this, the first thing you do is that you allocate buffers. Then you map the buffers on the network interface and populate the descriptors. Then the packet arrives. You have to sync it for your CPU. You have to sync the DMA memory for the CPU. You have to allocate a new buffer to feed the interface with a new buffer for the packet to arrive. Then you have to unmap the previous buffer if you synced it. If you unmapped it on step 4, you can skip 6. And then you have to push down the packet on the network stack. Now, when all this processing is over, usually drivers refill the descriptors of the interface. And the last step that is done is that when the socket is released, when the socket buffer is done with whatever the user space processing has to do, then we release the SKB. So if you think a picture out of it, this is not 100% accurate, and I think it's pretty hard to make it 100% accurate, but this is pretty much what happens on the current network path. Right, so you allocate, you map, the DMA transfer comes in, you unmap it, you do whatever you have to do on the RX completes, and then you free the buffer that you received, and you allocate a new buffer to refill the descriptor of the network interface. So here's what we're trying to do and how's the new path is going to look like. You'll still have to allocate the buffers. You have to map the buffers on the network counter, populate them. But when a packet arrives, you never unmap the buffer. So you sync the buffer for the CPU, you pass down the packets on the network stack, you refill the descriptors, and when K-free kicks in, when your buffer is about to be freed, we just feed the buffer back to our back to our pool. So we have a pool to refill buffers, and we never free them. The obvious caveat on that is that you have to allocate a bit more memory that you normally would, because on the previous case, you allocate a new buffer and you refill the network interface and you free the old buffer. On this case, you'll have to wait for the processing to end in order to feed the buffer back to the interface. So if the rate is too high, or if a socket fails, or if something slows down things on TCP or whatever, you're going to end up starving the network interfaces, and this is not what you want. So you pay some extra memory, you get some speed. So this is, compared to the old path, this is what you're going to do. You're going to allocate, map, the DMA comes in, you sync, you do the RX is done, you have to sync the buffer back to the network interface now, because remember, we're not unmapping anything, we keep everything mapped. So we only do sync operations, which is on coherent buses, this is pretty much free. So here's some problems. The first one is what we discussed. You need to allocate more memory. We explained why. The recycling scheme at the moment is based on a kernel's page pool API, which is only used by a single network interface at the moment, and this is Mellanox. The problem with this is that you allocate a single page per packet. And that's a requirement that you have. Now, Mellanox overcomes this because it splits the page and it fits 2 packets on a single page. But we don't do that. So Mellanox doesn't use our DMA capabilities, it just uses our allocating capabilities. They get the page and then they manage it and do the recycling in the driver themselves. As you can probably understand, both of the above needs that we need more memory. Now, if the memory pages that's configured on the system is 4 kilobytes, this is not too much. This is not too much memory to waste for the speed improvements you'll get. But if the pages are 64 kilobytes and the system is embedded, then you might start having some problems. What we're considering of adding the page splitting ourselves so we can facilitate many packets on a single page, but this is going to be relatively hard compared if you think of the interfaces that we have. And yeah, we really want to avoid that. Yeah. So we did some tests on it, and we tested it on a Cortex A53. We used the Marvel Espresso Bin device, which is a small embedded device with a driver, and the device didn't give us exactly what we wanted because there's a problem there, and all the queues end up on a single IRQ, so they end up on a single CPU, and we can't split them. But here's what we got. We got more than 2 times the performance of specific workloads, and I'll explain what specific workloads means. And the hardware doesn't have an SMMU. So if we try it on a hardware, with SMMU, we're expecting to get even more speed.
Question: is this just from the allocation and freeing that you save, or where does the improvement come from if you don't have an MMU?
If you don't have an MMU, yeah, it's just I'll explain the whole path. All right. So this is to visualize the performance improvements that we got, and I'll explain what the numbers mean in a bit. So as you can see, we're slightly higher on 64 bytes, slightly higher on 128, slightly higher on 256, and then there's a huge gap on 257. And then the gap is the same on 512 bytes, gets smaller because right now, above 1024 byte packets, we're really close, and we're really close on reaching line rate. So on 1,500 packets, we're exactly on line rate, and this is why there's no improvement anymore. So the reasons for the performance boost that we have. First of all, the driver is recycling the buffers instead of allocating and freeing and all the time. Now, the reason why you saw that the 250, the reason why the up to 256 byte packets, the performance is that, and the reason the 257 exists is that the driver is doing something that we usually refer to as copy break. So what it does is that if the packet is less than 256 bytes, it copies the SKB and does the DMA unmapping and does the recycling on its own. So it unmaps the buffer, but it doesn't free it, and it does the recycling internally. And that's the reason why on 257 bytes, where the actual driver path kicks in, where it has to allocate, free, unmap, and do the whole processing that we discussed, that's why the performance gets that higher over there. The problem is that we would actually expect the driver to outperform our solution on the copy break case, because since it's doing the recycling on its own, and we're doing the recycling with some extra function calls, how do I outperform the driver even there? The explanation is that the driver needs to copy the buffer in order to do the copy break. So it copies the memory on another location, and then it recycles the current buffer. And the copy that it does is the reason we outperform it even on smaller packets.
The buffer is always uncached when you copy it, which just makes it really expensive.
Another reason is that we rewrote part of the RX path of the driver. So instead, the traditional way of allocating buffers and mapping them to DMA is allocate the buffer with netdev alloc SKB align instead of build SKB. But build SKB is substantially faster because you just wrap around the data that you have pre-allocated. So that's another reason for the performance boost we got. Now, page pool is not perfect. And I'm not trying to say that it's perfect. That we have other problems. For example, if the recycling patches don't kick in, page pool is slower. Because when you allocate netdev memory from netdev related functions, you allocate it from a known location, and the fragment allocation on the network drivers is usually way faster than what the page allocator is. So if you take a normal driver and switch to the page pool API, first of all, you'll have to spend the page for its buffer, and second, your driver will be slower. I don't know how much, because it depends on the driver and how your platform handles the memory and the pages, but it will be slower. There was a bug fixed on really newer kernels when we released the page allocator memory to, instead of per CPU, we released it back to the body subsystem. So the hit is substantially lower now, but there's still a hit if you change to the page pool allocator without the recycling patches. All right. Now, the next steps. Another great advantage of the page pool and parts of the reason why we do this is that this started out of XDP. And XDP has a requirement that it needs a single page per packet. And this is a hard requirement. This is not going to change. This is related to how XDP works, how BPF filters work, how the requirements on pages. So part of the reason we want page pool to work is that you can code your XDP functionality really easily on the driver if you allocate the memory with the API. If you don't allocate the memory with the API, there's a bunch of issues you'll come along, and it's pretty common, and we're trying to fix it on all the drivers. But we keep fixing the same problems over and over again on the same drivers. So we did post an RFC, and people did like the patch. Almost. All right, this is a bit more technical. Right now, what we're doing is that we have an extra field on the SKB where the recycling information lives. So this is where we store what we should recycle, where we should sync our buffers. So when K-free SKB kicks in, we intercept the call of K-free, and instead of freeing the actual memory, we return it back to our pool. This is how this works. This wasn't the best approach we could have, because there's problems when it's a single linear SKB. This is fine, this is working perfect. But if it's not, then SKB spans across multiple pages, and we don't have the information to respond to recycle the multiple pages. We simply don't. So we have to unmap them somewhere, and if we have to unmap them, we have to intercept every driver or every kernel path that does the fragment allocation for the SKB, and this is going to get messy and ugly looking on the code. So we managed to merge something significantly good on the struct page. We have the DMA address in the struct page at the moment. So by moving the recycling information in the struct page as well, which is probably doable, is going to give us, okay. By moving the recycling information in the struct page is going to allow us to do that because we have access to the page from pretty much every path of the kernel, and we can recycle fragments, we can recycle jumbo frames, we can recycle anything we want. So we won't have to go and hack the kernel in various places to unmap buffers that were not going to be recycled. You can find all the sources you want, and you can find kernels that you can test this, and you can find the patches that you can pretty much, if you apply the recycling patches and you rewrite your driver to use page pool instead of SKB allocations, you can test this. And the page pool is not that hard to get it right. It's pretty simple to get the calls correct and allocate the memory for you. But so if you apply the recycling patches on top of that, you will get the recycling for free. What about? That's pretty much the same. I think it lives on fragments, so this will probably be recycled as well. This is part of the things we're currently testing at, and this is part of the things we're trying to figure out that we're not doing something wrong. And we haven't tried on the problem is that we're trying on 1,500 byte packets on a single gigabit interface, and we're reaching line rate. So if we do even bigger packets, we'll still reach line rate, and the device can do that. So we don't have a means of understanding if there is a boost or not. We need faster network interfaces and faster devices to
slower
You can
CPUs.
fragment it, right?
Right.
I mean, you can take the 1,500 to a fragmented packet and see what's the boost, but
if there's a boost between the fragmentation or not. Yeah.
if there is a penalty or not. And what about the, well, the penalty is basically the memory that you're going to need to allocate, because now you're
Yeah.
going to.
Yeah, it's the allocation, but I don't really think that the allocation is what hurts you the most. I think what hurts you the most is the constant DMA mapping and unmapping, because the device we tested happened to be non-coherent. So there was 30% of the use case was invalidating caches.
But can you allocate it on the run? I mean, once you see that you don't have enough memory, you can continue allocating, enlarge the pool, increase the pool.
No, this is not a feature we have. So this is obviously a problem, right? Because you have to estimate how much extra buffers you need to fill in for the use cases of delayed freeing packets, and yes, you can't probably guess everything. That's why we're considering on making it configurable. But growing the buffer is also an option. We're also considering that. Yeah,
Shrinking.
yeah. We consider shrinking and growing the buffer as well, because frankly, some allocation and some freeing during the operation are not going to hurt you too much. So you're still going to get most of the speed improvements.
So you've done your testing on A53 with with gigabit.
Yeah.
What kind of have you done any testing on a a more capable system with bigger line speeds?
Okay, we're currently trying to run it on a Broadcom and a Mellanox MLX5. So the MLX5 is probably going to give us the results we want. The Linux kernel maintainer for Mellanox already has the page pool in. All he has to do is I need to go back from connect. He needs to apply the recycling patches and give it a spin. So probably next week we'll have more information on this, and since this is pretty critical, because if we do something wrong, we're going to blow up too many things that we don't want to. We're practically going to blow up networking. So we do intend on testing it too much on high-speed interfaces before going ahead and say, hey, use it, this is good.
Cool. And so on the bigger interface, bigger devices, you're going to be doing a lot of jumbo frames and that kind of thing as well. Yeah.
The jumbo frames work. I did manage to test the jumbo frames here, but there was no point in putting the numbers up because it does line rate equally, so jumbo frames was going to be even worse. But the jumbo frames in the kernel is that the kernel does fragments, right? So it allocates an SKB and then it adds the fragments on the shared information of the SKB. So that's what we had to test. We had to test that we recycle fragments as well on jumbo frames, and this is working now. If we move everything to page, this seems to be fine.
Awesome.
Anyone else? All right. If you need anything, any help on the patches, thank you.